This
Can you all see
conference
that
will
screen?
now be recorded.
Yeah,
is that
Ben.
screen open? Excellent, excellent. Okay, so thank you for letting me give a talk at the PWI. What I'm going to be talking about is research and development into alternative formation treatments. This is work that I've been involved in myself as part of Network Rail's R&D program. So there we go. So what we've got is we have a challenge, and the challenge is how we can improve the performance of our track assets. So the track is a system, and it responds to a range of influences, such as loading, vehicle speed, water content, temperature, all sorts of things, vegetation, the amount of traffic, huge amount of things affect that track system. And what I've been looking at is the formation side of that. That's the bottom part of the track. I'm not going to try and get into giving you a lesson on what track is constructed of and how it's constructed, because I'm sure most of you are more than aware of that. So what we do know is we know that a resilient track formation leads to a better performing asset. And if we've got a better performing asset, we reduce the need for maintenance intervention. That reduces the cost, increases availability for the running of trains, and improves safety by not having to have people out there on the track. So if that track system works as it's supposed to, the track componentry is able to perform for its full system life. And I've used an image there that just shows you some of the sort of changes in the track geometry as it goes down that long line there. So the bottom part, the formation, largely unchanged since construction, and it was constructed using the technology and understanding of the day. In various areas around the country, mixed materials of various stiffnesses were used, and these pockets of different types of material can result in changes in stiffness over quite short spaces. And at the time, we had lower speed vehicles, lower axle weights, with fewer trains. So the deformations, they tend to depend on the stresses being placed upon the track and the resistances that occur within the soils and substructures. And these are determined by things like layer densities, thickness of layer, and the deformation modulus of the material. So if it's really sort of poor material, it's not going to do a very good job. The deformation modulus as well is also influenced by the water content, and we can, to a certain degree, manage water content. I mean, at the end of the day, we all understand that water is, the enemy of everything and what we do. And we'll always find a way into getting into things. So that's the challenge. That's where we're looking at. We want the track to perform better. Some people look at the rails and the fasteners, the sleepers, and what I've been looking at is really the sort of the stuff underneath there that supports that track superstructure. So how do we look into this? How do we go about approaching this sort of work? We can't all sort of go crazy and pick any idea we feel like and run with it. It has to be organised. So what we have is an overriding rail technical strategy. That's an industry document with Network Rail and the RSSB and various other partners. And I've put some links up there if you wanted to go and look at them yourselves. So that's the big overall document. The challenge statements, again, the challenge statements are created to support the technical strategy, and they give a bit more detail on the definition, root cause analysis, priority areas, and basically a bit of guidance for R&D for those areas. The challenge statements are drawn up with input from the rest of the business as well, and they're available out on the Network Rail website. And then a bit below that is Shift to Rail. Shift to Rail is an EU project that delivers through railway research and innovation capabilities to bring about sustainable, cost-efficient, high-performing, time-driven, digital and competitive customer-centered transport mode for Europe. A long sentence there, and to do it justice, I had to read that one out there. So effectively, Shift to Rail is a European collaborative project. It's an umbrella project. It has many projects within it, and it directs research, R&D, topics, strategies, aims, and brings people together to do that. So we use that through Network Rail as a vehicle to further our own development. Now, once we've got those challenges and we've got the mechanisms on how we're going to do it, what we need to do is really look at how we sort of organise the approach to R&D. Again, we don't want to go running off and spending money in areas that we don't need to, and equally we need to have a structured approach. So what Network Rail uses is the technology readiness levels. These were a system originally developed by NASA back in the 1970s and is used to estimate the maturity of the technology. So you can see each of those stages takes a step up, you test it in its next environment. If it doesn't perform, you go backwards and you modify and you change. And this particular example is obviously modified for use in the Horizon 2020 program, which is part of Shift to Rail. So the European stuff to guide everybody out there doing the research to be able to peg it to certain levels. So that being said, we've got a challenge, we've got an approach on how we're going to do stuff. So what did I pick? The area that I've been looking at is asphalt track. Now, there are lots of different types of formation treatments already out there. We've got geocells, geogrids, various types of track membrane. There's all sorts of materials, techniques. And what we want to do is develop a range of options, because some of those options are suitable for certain environments and some aren't. Sometimes you need a more resilient type of, sort of treatment there to go in. Asphalt's not new. I mean, British Rail looked at this a long time ago, and it's gone in and out of favour as the requirements of the railway have changed, and we now sort of coming back, and this is used a lot across Europe. So asphalt track, basically, it's that layer of asphalt below the ballast, and it's there primarily to distribute the load and reduce the stresses in the soils. And if we reduce those stresses, we can reduce the amount of differential settlement. If we've got a nice uniform track structure there, it maintains the track geometry longer. That reduces the need for tamping, which again prolongs ballast life. It controls the groundwater, reduces ballast fouling, and it can be recycled as well. So what we get is some of the benefits of a slab track system, but without quite being a slab track system, and we don't have that permanence there with that. So as we go on, here's an example, right? So I'm going to jump straight in with an example of some nice pictures. What you're going to see is quite a lot of pictures. There is the odd slide with text. I tried to keep it a bit away from that as much as possible. So this particular example, to say we're not doing it from new, because R&D isn't always about coming up with a brand new idea. Sometimes it's about innovation. It's about taking things that are done elsewhere and modifying them and using them for what you want to do. This particular example is the Nimes-Montpellier bypass, completed in 2017. And what we see there is a road that's been constructed with a lorry and a tired crane on there, sort of cherry picker type arm, dropping off materials. Excuse me. Effectively, what they did out there, they built an entire railway. This is an 80-kilometre length of track. It's mixed speed, so it's mixed use. It's freight and high-speed traffic. 80 kilometres in length. They built it effectively as a motorway, and they built the railway around that. And what that did was gives them a twofold advantage. One is that they get a resilient track structure. Now, bearing in mind this was done in a greenfield site as well, so this was new. This is they did have a bit of time, but equally it was a huge piece there in delivering the project very quickly. A huge part about railways is logistics, moving things in and out of sites, constructing, using trains, using all that sort of stuff. Here they've been able to use lots of vans, lots of lorries, lots of diggers, tired vehicles, much easier, and they can work around that. So there you go. And then as you can see there, what they're using is a paver to drop a layer of ballast onto the top of the asphalt there, and equally that using a paving machine, you don't always have to put asphalt through them. You can put stone on that. I think it's particularly brilliant for them. Excuse me. And it also adds a sort of layer of compaction, uniformity as you go along there, so you can get a good degree of construction quality. And there we go. There's a picture there of a rather large French freight train on there. And what you can see is the ballast and the track there on top of that asphalt layer, and how it goes out there. So, and that ballast layer extending out the side. So that's a previous case example. Now, where we came into from the UK's perspective is we don't really build 80-kilometre lines. I mean, we do build lines here and there, but we're not really building new lines. We tend to be, maintaining our existing assets and existing tracks. And there are bits, but that we do, but not on the scale that they do in Europe. So we recognise asphalt works. How can we bring asphalt into the UK? Well, what we want to do is bring that in as a retrospective treatment to formations. What we have is that poor formation where if you were to try and rectify that, if you really want to get into the nuts and bolts of it, you'd be taking the track up and doing large amounts of excavation. And we don't know where once you start digging, you don't know where you're going to end. It's very time consuming. It's very expensive, and that's just not really palatable for what we do in the UK. However, we can use asphalt, and rather than replace some of that material in the formation, we can use it to sort of bridge the loading there and reduce that stress. So the material may actually be able to perform and continue to keep that track geometry. So what we did was, obviously following that TRL level and using the shift to rail projects, we ran a piece of work at Heriot-Watt University up in Scotland, and this was a lab testing, and what we wanted to do was simulate an area of weak formation, like a wet spot type area, and we wanted to apply a cyclic load to that, and we were going to compare the ballasted asphalt and against the ballast to really see what the sort of potential benefits are. I mean, lab work is never fully a real world example, but it does give you a strong idea. So what I did was, and again, I'm going to get, this is quite a brief overview of some quite long, complicated bits of work. So what we've done there is we built a big test box. It's a big metal test box, looks like a skip. In the center of that, we've used some matting to simulate a weaker area. What we've done there is we've now compacted, we've used compacted type 1 material either side of that to pack that in. And then what we've done is on this particular one, we've placed another layer of that type 1 material over the top. And then what you can see there is a row of asphalt strain gauges. So those strain gauges embed into the asphalt, and as we go there, so you've got ones at the end are looking at solid material, ones in the middle. The two inboard ones from that are really sitting towards the transition, and the one in the center is sitting over that right in the middle of that softer area. So the next one there, so sorry, apologies. So what we have there, we now have that asphalt layer compacted on top of that. So you can see that's the sandwich there. That's our formation sandwich that we're going to put into the rig. What Heriot-Watt has is a large rig called the Graph 2 rig, and this allows for the simulation. What we can do is we can fit large amount of hydraulic actuators above that, and we can build a track section above it. So that's quite good. Hold on 1 second. To clear my throat there. So we took that into that. Next slide. And there on top of the asphalt, as we were building that, we installed pressure cells. So those pressure cells will tell us what loads are being transmitted down. Here we go. We're building that in, and what we've done here is I've used I had some sleeper type shapes constructed. These fit to the rams, the actuators rather, and you can see the white tubes there as well. So what we did was we fixed sort of poles to the asphalt surface. And if we go on to the next one, there you go, you can see it constructed. So what we've got there is we've got those we've got the strain gauges in the asphalt, we've got the pressure cells on top of the asphalt, we've now got the our sleeper set up. Each of those actuators are instrumented. They're very, very fine instruments on that. And then on top of those white tubes, we've got a range of LVDTs, which will sort of pick up various movements across that. And then what we did was we put a loading cycle through that, where we stepped up the loading at various stages and measured it, and then we carried on and we went through and we did a considerable amount of load through that to see what we get. So what we've got there is, and I try to avoid graphs and all that sort of stuff, but it is a quick representation of what we sort of achieved. Was you can see the two lines going off there. That's basically the ballasted version, the red and the blue towards the bottom, and you can see how over the sort of MGT value there's been a degree of settlement. And then if you look at the two above, that was when we used the asphalt situation, and you can see how closely they are and how they perform together, and how the settlement there, and you can just see the sort of dips in each of those grades. That's when we stepped up. We took quite a big significant step up in the loading. So that sort of gives you a brief indication of what that is. Apologies for a text one, and I'm sure you can, if you really want to read it, you can come back. So what we found at the end of the day, the conclusions: the asphalt layer helped to bridge across that low stiffness and subgrade transition zone. We generally went from 40 kPa down to about 11.7 kPa. It's about a 72% reduction, and this was due to the asphalt spreading the load over that wider area, and it shows the ability to absorb some of that loading as it goes through. So what we did was we reduced the track settlement, particularly in the presence of low stiffness subgrade, which is what we were trying to prove. And that shows you. So what you're looking at is effectively like a sort of a frog on a lily pad type thing on the water. It's about finding the optimum size lily pad to reduce the weight of that single point load over a wider area. So moving on, we took this into another area. So we went to York Sidings, Skelton Yard. And what we wanted to do now was we proved it in a lab. We've said that's great. We understand that there's some clear benefits there in a week. We already knew it worked in the new build construction. That's been proven. We've now got lab work telling us that it sort of works in soft formation areas. So now we want to have a look at constructing it. So we did this piece of work there, and there's some pretty grim photos, but I make no apologies. So the first one there, that is the area we got. And when I turned up and saw this site, I thought, crikey, this is going to be a challenge. So working with Tarmac, they were great in helping us there do that. We had a site. What they were going to do is build some freight sidings up at this yard in Skelton, and we were allowed to go in beforehand and do this. So this is not mainline. This is within a siding that had been ripped out and was going to be reinstated. I believe a lot of the material that was used as we were going there was old ash out of the steam trains that had been dumped from York Station, which was just around the corner, and probably used in that area. And then what had happened was there's a lot of rain there, and it's got very waterlogged and very compact. Now, realistically, that's good in some respects, because what we're doing is we're trying to say, look, we want to build this, and we want to build it over absolutely rubbish ground. And there you go, we've got an absolute awful piece of ground there. And you can see where we've driven a vehicle across it, it's just chewed it up. So here's a few of the pictures from what we did. Thankfully, we've got a lot of time and space, which we don't have normally. So we've got a lot of time and space, and Tarmac turned up with an awful lot of type 1 material there. So we were able to spread that out. And there you go, you can see we're dozing it out and getting that ground sort of stiffened up. And it really was bad ground. That was really poor material. So ideal place to test it. So we got that out. We've now got that line of MOT out. We've got that compacted. Excuse me one second. So we've got that MOT base set out, which is great. And what we now are using is a paving machine to come in there. Now, what we've got there is a tracked paving machine. There were a lot more photographs showing a lot more things, but I didn't really want to show you the horror photographs. But needless to say, we got in there and did that. So there you go. We're starting to get that layer down, and we're getting that asphalt. There's a bit of a run in there, and it goes in, and there you go. You can see that layer being put in and laid out. And the machine itself does compact to a certain degree. and then ultimately that was the test section we got built. Now what we did do there was we tested a couple of different thicknesses, and we got that, and then there was a track reinstated. So there was the picture of the track reinstated over there. It was a bit of some time later, as you can see some of the regrowth in the vegetation around the sides. There was a separate piece of work that went off, that went there. Now, unfortunately, that wasn't as successful. Whilst it demonstrated the benefits, what they did was they retrospectively installed a number of sensors. Now, when you do that, you disturb the environment you're trying to measure. You know, we want to look at long-term consolidated tracks, and the second you dig a hole in it and put a sensor in, you've disrupted that environment, and you won't get the same level of compaction. So there was a bit of a lesson learned there from that. However, that, you know, what I'd set out to do was to basically demonstrate the construction in poor material. We've done that, we achieved it, and we said we can build it. And then that subsequent testing afterwards did indicate a degree of improvement. And you've seen the sort of ground conditions. So I dare say people out there are pulling faces at what we're trying to build on top of. So moving on, this was a big piece of work we've been involved in recently. So we've got to take it on a stage, take that R&D. We're growing, we're getting confidence, we know what we're doing. So what I wanted to do was, as part of one of the Shift to Rail projects, was I wanted to build a technical demonstrator. We wanted to upscale that and put it into a real world environment, get some real data and prove what we were trying to do. So there's a couple of aims there, which was to demonstrate the use of asphalt in an operational environment, and I've already explained why we were doing that. Is to collect and provide data to support a performance evaluation, because we're all the time we're measuring and we're trying to understand what the benefits are and how it's going to improve things. And we wanted to provide data to support various models. There are lots of universities we work with who produce all sorts of models to the best they can, and they use that. They love to get a bit of data, real world data, because that will prove whether that model is working or not, or it allows them to develop those models further. And getting real world data is quite difficult at times. So this is a great opportunity to jump in and do that. So and another part there was to demonstrate the use of advanced embedded remote performance monitoring technology. So we put a huge amount. I mean, I really wanted this thing to be instrumented and talking. So working with the University of Southampton again, and Tarmac were very helpful in being a part of this. We designed a comprehensive instrumentation setup. There was no, it is a really good opportunity, and they don't come along all the time. So we wanted to get as many things in there as we possibly could. So moving on, this is what we proposed. A bit of a sketch there. What we had was, I went out and we did a whole load of work about approaching various track rams around the country, asking for sites, because for me to go and do this off my own back is hugely expensive, and these things take an awful long time to plan and put together. So what we wanted was sites that were already planned in, work that was already planned in, that offered us a good opportunity to piggyback on. And we found this site at Leominster. It was due for a renewal. They were doing some work through the platform to reduce the track bed height, but there was a considerable amount of runoff at the end as they graded back into the existing track. And that section of track was a fantastic area to get in, not least because it offered us brilliant access right up alongside the track. I mean, that is one of the real difficulties when you're doing anything like this, is you don't want to be lugging materials miles up and down, because it just adds to the complication. We want to keep it as simple as possible. So what we've got there is obviously a transition in at one end and a transition out at the other end. That is effectively the length of renewal. And in that, I said, can you dig a piece of track a bit deeper to allow me to put this asphalt back in, bring it back up to the same level we were at before, and then you can rebuild your track on top of that. Now, there were two areas of instrumentation: control instrumentation and then asphalt instrumentation. So there you go, and there's some mileages giving a bit of an indication of what we want to do there. So that was the cross section we came up with. 250 mil of ballast, 120 mil of asphalt. Now 120 mil of asphalt is good because we can do that in one layer. Keeps the time down. We know 120 is good, and we're not doing multiple passes. The type 1 we wanted to extend out, to take the rainwater away, really from any sort of water coming down from above, take it away from that asphalt type 1 interface and allow it to sort of soak away in the ground to the side. In this particular case, the drainage wasn't being installed in this particular location. So transitions are a big thing there. We wanted to make sure we got the transitions right, and I went across to our trackbed investigation team, and I believe those guys will be talking to you in the next few weeks. And I asked them to help me design and prove the transition. Now, we could just go for the standard transition sort of approach, but I thought, well, we really want to sort of make sure belt and braces we're doing what we need to do. So there's a bit of a simulation model there. You can sort of see the difference in pressure seen from a ballasted track to a non-ballasted track. And again, they took a huge amount of stuff in. A bit of a graph, what we've got there is that transition zone going from the conventional formation across to the asphalt formation. And we modeled 4 lengths. We did a 0 meter transition, 5, 10 and 15 meter transition. And what you can see is 0 and 5 are pretty close to each other there, and 10 and 15 are pretty close. What we opted to do was we opted to go for that 10 meter transition in the end due to the similarities in performance and obviously the space requirements and complexities of construction. Here's the transition design itself. It's a bit more complicated than usual. So we've got that type 1. We've got the asphalt and the short running. Obviously, it looks quite steep there, but when you put it out on track and you spread it out, these are very slim wedges. But what we wanted to do was backfill that type 1 around the transition, and we ran the. What we did was we included a geo grid. 5 meters out into 5 meters in, and we ran the geotextile that was being fitted with the existing renewal straight into that as well. And what we wanted to do was avoid sort of sinking and pooling and collection of water around that area. So we really stiffened and bridged that across, and that's a really good solid transition design. So we get to the day of the build. I mean, we went through a huge amount of planning and discussions and safety validation and all the systems and processes, NRAP, CSM, all planned out. But obviously you get to the day and you're going to get challenges. And, for my sins, I got pretty much most of the challenges you could possibly get thrown at me. So we've got it planned, we've got the time, we've got the people, we've got the equipment, we've got everything ready. The alliance has gone through. They've dug down that track bed down to the area we want it to, and we've found this large pipe running down the centre of the track. So that would have obviously been in the 6 foot long metal pipe. Nobody knew it was there. It wasn't detected on any of the surveys. Been there for quite a while, so not particularly brilliant. That obviously causes a few delays, and every time you get a delay, I'm thinking this is going to eat into what I want to do. So that pipe then, not only did it run down there, which was fine, wasn't bothering a lot of people, it cut 90 degrees across the piece of track I wanted to go into. So right in the middle, and the ground around those pipes, in actual fact, there were 3 pipes. That's the 90-degree one that was still attached to the center pipe. There were 2 others that we managed to dig up, which were not connected. But as you can see there, that's gone. You couldn't have placed it in a worse place. It was right in the middle of the bit I wanted to be in. Obviously, when it had installed, the material in that area had changed as well. So we've got really soft filled back, material from all over the place. None of the nice material we got either end, which had given me loads of confidence. But on top of that, at the same day, so you can see obviously that water there getting in, and then I'll go across to that, and you can see that there, that pipe running down and then running across right in the middle. Now, when I got to this stage, this was on record as, and it really doesn't show it here, but this was, according to the Met Office, the wettest day in the UK since records began. This work was happening on a Saturday morning. It started raining Thursday and it didn't end till probably Monday. The ground was absolutely saturated. And as you can imagine, when you start digging a hole, all that water then starts coming out the surrounding areas into that area. I couldn't have really picked a worse area. None of us knew that. And when we did the track bed investigation, that particular piece was just not picked up. And I'm sure people in the construction world completely understand that you find things all the time. So that was not good. And there you go. You can see a bit more rainwater there, and it's just filling it up. It's just pouring in and getting everywhere, and making things very, very difficult. So there you go. In the end, no. So not only did we have pipes we'd not found, we had exceptional weather, and we also had some plant issues with the dozer there. That was having some issues with its levels. Now, one thing we were able to do was we were able to improve that area around there. We had materials on hand, we had the people and the skills, and we were able to sort of tackle that area. What we believe those pipes were potentially old water pipes taking water down to the station to top up steam locomotives. When we look back at some historical pictures of the area, you know, there were considerably more lines at the time running in and around the back, and in some old photographs you can see those water towers up in the background. So local sort of installations. They're not sort of gas pipes or anything like that. They would have been locally done pipes, and probably very, very little in the way of records to demonstrate what we're there. So all that being said, we got to a stage where we just couldn't install the asphalt. We'd done all this work, all this effort. We've been going at it for a year. I'd put everything into this, huge amount of effort trying to demonstrate that it's good, trying to get people on board. You know, it's just absolutely immense trying to do anything like that. And you know, everybody was really positive. We worked really, really hard. We did as much as we could, but sadly, we couldn't install that asphalt layer. Thankfully, we'd done remedial planning, and I'd got materials and items on site to allow that should we have pulled the plug at any stage, we were absolutely clear on what to do to reinstate that track and get it open. And thankfully the track was opened. We did get it back on board, and the track was open to traffic on time. And I dare say that we've also improved that area where those pipes were by stiffening up that ground underneath. So what did we do? So this is the interesting thing about R&D. You start off with a plan and you go through each of those stages, and quite often things will happen and things will occur and you will change direction, and it's how you continue to go with that direction. So it wasn't a complete loss. I'd got the University of Southampton on site with me. I'd spent a huge amount of money on instrumentation, and we took the opportunity. We said, well, okay, we're not going to put the asphalt in, but what we are going to do is we're going to use this instrumentation. We're going to put it in the ground because there is a tremendous amount we can learn about renewals and the performance of renewals and how effective renewals are. Now, this level of instrumentation has probably never been done anywhere else. It's really, really comprehensive. And what we've got is we've got two sections there. You know, the main part is really the one to the left, where what we have there is we've got pressure cells, piezometers and accelerometers in the formation, and we put that in the formation before we put the track back. We've got the geotextile layer going down, ballasting the geotextile. We've got more pressure cells in there, and then, you know, going up to sleeper level, we've got accelerometers on the sleepers, and fiber optics on the sleepers, and we've got fiber optics in the formation as well. Fiber optics, state of the art. Again, nobody's ever been putting them into the formation. So we have a section of track there, approximately about 8 to 10 meters, that is instrumented all the way through. And not only that, it can talk to us. It can talk to the internet, so we can pull that data. There you go. So that, I mean, that's taken us down a slightly different route. All is not lost. It's not, you know, that's R&D for you. So we've tested this. We've been out and we've done a test just to prove the system works. And there we go. We can sort of see these are example deflections obtained from an HST using the accelerometer system. So as you can see, as that train has passed through that section of track, we can see what the deflections are, how the sleepers are moving, and up and down. And you can see each of those axles as they've gone over, all the bogies as they've gone over that site. So that tells us what we're doing. And if we can continue to monitor that, we can start to trend what's happening. And not only that, we can then look at the pressures. So we can start looking at the pressures in the formation. So we know what's happening above, we know how the top part of the track's moving, and we now can see how this is going down and this is being felt in the formation below it. And when you understand how that works and how that deteriorates and changes and know about the materials, much better accurate understanding of what's going off. And the idea is that that can influence how we approach things in the future. You know, getting that, we've always done things because they've always been done, and we can now bring in the data, the science, to underpin that understanding, and maybe challenge a few concepts, maybe let us consider how we do things. Interestingly there, I mean, you can see the pressure reading from below, and that's from the piezometer, so it's exactly the same time. And what we can see there is that train, as it hits that site, you've got that spike in pressure, and then you've got that building of pressure, because it builds and builds and builds, because water's incompressible. It can only move so far, and depending on that degree of saturation, obviously as you load it, it takes time to unload, but you're already reloading it before it's had time to unload completely. And there's that build up in that pressure there, and you can see how it takes time to filter back out, but you can see those spikes, and again, there's some fantastic learning we can get out of that. And this is it's a difficult one to understand. This is state of the art, and we're developing this, and then again we've now created a platform to take this further. So using fiber optics, we can run them out on the rail, and we can run them out in the formation. We did run a longer length, but sadly we drove a digger over it, so it broke some of it. But that's how it goes. But we have got a section there, and what you can see is that's effectively distributed strain along the fiber optic there. So when you run out the piece of fiber optic, it becomes a really large strain gauge, which is really good. So moving on, there we go. There's some of the potential benefits from that site. So whilst we didn't build what we wanted to build, we have built something else, and there's a huge amount of benefits there, from talking about demonstrating how we you know, getting a lot of insight into trains and vibration and track bed and the interfaces, and how that can be used for models, how it can demonstrate you know, instrumentation. A big thing going into the future is obviously looking at how we instrument track, how we get that track talking back to us, how we can monitor performance and understand what's going off. So there's quite a lot there, and I won't obviously read it up word for word on that one. So, okay, I didn't build what I wanted to do. So the best thing we can do from that is say, right, do a lessons learned. And we did a big lessons learned, and we got a lot out of that. We were very frank to the point about it, and I got a lot of help from the route and the guys out there doing it, and also from various people that were involved in the project. So this all sounds very obvious, and we can all sit there and say, well, I would have known that, but we do this over and over and over again. It always happens, and people make the same mistakes, and it does, but we've got to drill it in. So if I was going to do a more advanced renewal, I think I would take more time and do a deeper site investigation. I think sometimes a standard investigation isn't enough, depending on what you're attempting to achieve. Sometimes it is enough, sometimes it isn't. You know, maybe that's a benefit. The existing road construction plan is not suitable. We hit a number of snags, even though we used various bits of kit. We found the plant wasn't quite suitable. Plant on the railway has been developed, obviously, over time to do what it's doing. The plant we used was absolutely excellent for what it was supposed to do. I think it's a bit about marrying that up into its new environment. Bring in non-railway specialists. If you're trying to do something new on the railway, and you're trying to bring in skills, because we should be bringing skills in, we should be bringing these technologies and skills from other industries into the railway and benefiting from them. But we've got to introduce people to that environment and explain to them what it is we're trying to achieve, and let them understand as well. So bringing people in earlier, getting earlier involvement is really good. The asphalt construction method. Now, I'd gone for a road. I was fixated on building this fantastically smooth road, and what we found is that you can't construct a fantastically smooth road on the railway, not in the time scales we've got, not with the materials and the plant we have. So what we need is a more rough and ready construction method. We found that out. We've done it. We tried it. You know, I dare say if we'd have had the time and it hadn't been raining, I could have built an absolutely fantastic piece of road to build a railway on top of. But we need to obviously approach how we do it. And I think what was obvious was that the levels of accuracy are not quite the same, and they're probably not needed in the same way as what you drive down a motorway on. And then detailed future planning and mitigation. You should, I mean, we did an awful lot of failure planning and mitigation and allowed us to walk away without disrupting anything. It didn't happen what we were trying to do, but that is just the way it goes. So where do we go from there? I mean, the next stage obviously is, and I think I'll take one step back. What is worth mentioning is, you know, we tried this in possibly the worst conditions possible, and we broke it. And there's nothing wrong with breaking things in R&D and not doing it. We stress tested it, we broke it. Now, if we'd have done it in a perfect world, it could have gone away. We could have told everybody it was great, and they build it in bad conditions and it fails. So you know, one of the benefits is what we learned early on, where we need to change what we want to do. So that was really good. I didn't feel like that at the time, obviously. I was much more sort of quite upset about the whole thing. But that is life, and that is R&D, and we move on. So where do we go next? Excuse me. Looking at advanced. So I've been doing some parallel work looking at S&C, asphalt under S&C. And if you were to ask me what my sort of future strategy would be to say, okay, as a formation treatment, if we'd have been able to build what we set out to build at Leominster, it would have done the job. If we could have got a compacted layer of asphalt down, it would have worked in that really poor soil area. It would have worked. The track would have been brilliant. We couldn't install it. That was the issue, not that it wouldn't have worked and did what it was supposed to do. So rather than keep trying to do the same thing, we've got to look at what the business needs and what the business wants. So I would go towards S&C. I personally believe that given the issues that S&C faces and the issues with differential settlement, some of the failures of S&C are linked to formation, some are linked to other parts of S&C, which are probably influenced heavily by formation and the lack of maintenance and techniques we have to do that. They're very difficult, complicated pieces of kit with many more dynamic influences. I would move to put asphalt under S&C as a sort of raft. I think the benefits would be quicker achieved, and I would prefer to have the track floating, S&C almost pegged on an island with a really solid formation. I'm not saying I wouldn't use asphalt in plain line. I think it absolutely works, but obviously we've got to direct our R&D because we don't have an endless budget. We don't have that sort of stuff. So where can we get the most amount of benefit from our work? So the next part is really future directions, looking at instrumented track. There's a couple of two acronyms there: Internet of Things and big data. So what I've built demonstrates a bunch of instruments that can talk to the internet. We can log on and see what that track is doing remotely, and we back that up with real measurements, and you've got a fantastic piece of kit there. Internet of Things is about using cheap, readily available instruments, plugging them all together, you know, putting them out in a field so there's plenty of them, and getting that data. Big data, you've probably heard all about taking that data in and analysing it and using it to tell us things. And the more we get, the more we understand, and the more we can sort of draw conclusions. Cold asphalt. Now that's something that you know, is potentially removes an awful lot of limitations. Looking into cold asphalt can be stored and moved a lot easier, a lot quicker. Held, you don't have the heat implications, the time constraints during renewal, and not only that is we could you know, move that around a lot easier, probably a lot less plant requirement. looking at one cold asphalt supplier recently, that was 40% reduction in carbon over a standard asphalt. So, you know, these things all amount to, you know, helping develop the business case for using them. And then simplifying the installation method. Had I brought, you know, tarmac in much earlier to witness standard renewals, I think we probably would have adopted our installation method and gone for a more sort of almost sort of bucketing, using a digger and bucking it out, cold asphalt, and pushing out with a laser guided dozer, getting that layer, giving it an install, you know, really sort of rough and ready, but still doing what it's supposed to do. So that being said, what are the challenges to R&D? And these are a lot of the challenges I faced along the way. Funding, thankfully, we got Shift to Rail, and we used an awful lot of European money there, and we satisfied their aims and also aligned that with our aims. We might not always have these R&D projects. Timescales, again, renewals are planned very, you know, quite far in advance, and the project timescales don't always align with that. So that makes things can make things difficult. Working for the long-term benefits, people want things now. You know, we want the benefits now. You know, and I can understand why people want that, but equally, you know, if we want to be building a better track, then we are building things that might be 30, 40, 60 years into the future. And if we use some of the technologies now, we'll push things out even longer. So whilst we don't see the benefits immediately, you know, it does as a nation. So, and then also allowing flexibility to try new things. So a lot of the asset managers are constrained by a lot of targets they have to achieve, and sometimes we have to allow flexibility to do the R&D and remove some of those, you know, bits we hold them to open the door for that. So in short, I mean, that was a path through some of the R&D I've been doing. You know, that's taken several years to do all that work, and there's been a lot of people involved, and I think everybody along the way has been incredibly supportive and open, and it's just about changing the culture and changing our attitudes and trying to open the door to do these things, you know, because we can only fix so many things above the track, and the benefits become less and less, and we need to start getting into the bits underneath really to sort of, you know, make that step change. So there's a couple of references there for the images, and hopefully that gave you a brief insight into some of the stuff we're doing. So and there's my name if you want to talk to me about any more of that, which is always welcome. I think
that's brilliant, Ben. Yes, thank you very much.
47 minutes. I think I tried to get that on time.
Yeah, no, that's brilliant. You know, the presentation interesting. So let's open the questions now. So if anybody's got any questions, if you put your name on the chat, I'll pick it up and call you to ask a question to Ben. I've got a question from right at the start of your presentation, actually, waiting for other people to chip in, about Shift to Rail.
Yes.
What is the future then of R&D funding from Europe, considering, you know, the situation with Brexit?
So Shift to Rail at the minute, like I say, there are a lot of projects. I mean, the bigger project itself is called Horizon 2020, and that covers quite a lot of different sort of forms of transport. And then we get to Shift to Rail, obviously is more rail focused. We're just finishing a project at the minute called Intertrack 2, and we are about to start a project called Intertrack 3, which will take forward some of those technology developments. And that's not all about formation. There are a lot of people involved in that, and I believe that there are future projects being considered in Europe as it goes. So there is work, and that work in Shift to Rail also aligns with some of the other university works that are going off as well. So we have a number of specialist university institutions also looking at research.
Brilliant. Thank you, Benjamin. Matthew Kaler, would you like to come in and ask your question?
Can do. Thanks, Fred. I just wondered what the cost impact you see of the instrumentation that you looked at. sort of the availability to roll that out and how quickly that would be recovered in terms of the whole life costing within the asset management.
The instrumentation we placed at that site is very comprehensive, and it is quite expensive. However, some of those technologies, if you were to deploy elsewhere on the track, aren't as expensive, and the costs can be reduced. And again, I don't think there's ever been the idea that we instrument. Obviously, it would be great if we could instrument the whole network, but I think the ability to deploy, almost like a mesh of instruments to problem areas is really good. And I think the continuous monitoring is really good. And the ability to pull people away from track and pull people away from doing inspections is really good. For example, the accelerometers, they're getting a lot cheaper. The fiber optic is in development, and the fiber optic itself is very cheap. The interrogation is a little bit complicated at the minute, but again, can be deployed. And then the ability to, bring that into using it as part of the internet, that connectivity is what's really being developed and what really unlocks a lot of things. So yes, there is a cost at the beginning, but that cost is coming down. The benefits are reaped quicker because that continual understanding of what your track's doing and the ability to react to it. So all good. Does that answer your question?
Yes, there is a bit of work I'm involved in leading from the track viewpoint, which is related to fiber optic, use of redundant fiber optic cables that exist on the network, picking up use for a number of different things. So it could be useful to discuss that with you, because that could be technology that's already being developed and used and you could piggyback on. I
think it's the ability to not just do it for track, but to do it for structures or embankments. And it's the ability to use plentiful, cheap, connected instruments to understand what the assets are doing, even if it's just to highlight you and get you out there. And I think the example there is probably hot weather and rail buckles. And at the moment when we have to put people out there to monitor track, if we can take people away from that, that's very quickly pays for itself.
Yeah, thank you.
Are there any more questions for Benjamin? No, that seems to be in. But just start now to thank you very, very much for coming today and do this presentation. It was certainly very informative and very interesting, and certainly, raise some ideas in my own mind about how we can best use the technology, certainly on problem sites when we do track renewal, to keep monitoring. We've got this remote control monitoring now that has been laid out, certainly for signaling equipment and other. And I've got a feeling that the type of equipment that you use, although the cost may be an issue, but it could be a way of actually better understanding the performance of our assets and be able to react, before things go wrong.
I think a part of what I was trying to do was sort of show people that there are people out there looking at these sorts of things, because part of it is about sharing it with the rest of the industry, because that may give people ideas where they can jump in, or they can help, or they can adapt it, or they can take it for their own use. So a big part of that is trying to get that sort of visibility out to the rest of the business.
Yeah, and I think you've certainly done that today, Benjamin. So on behalf of everybody on the call, I would like to thank you again for your presentation, taking the time to come on and speak to us. And for everybody, our next meeting will be in 4 weeks' time on the 19th of May. Change of subject. We remember that PWI is about infrastructures, and certainly electrification is big part of the PWI agenda, and we'll be welcoming Darren Tiddy from the Western Route come and talk to us about about pantograph monitoring. So I hope to see you in 4 weeks' time, and thank you again for attending today.